All right, let's get started. Forgive me if I'm moving a little slower than normal today. I'm getting over a cold, so, sniffly and lost energy. Y'all know how it goes. I was walking through the halls. I kept seeing people sniffling. I'm like, it must be going around. So, yeah, I heard, I heard some sniffling. Okay, so a couple things. So homework 5 is due today. Your weld homework is due today. I'm going to try and get that graded over the weekend. Worst case scenario, on Monday, I will have a copy of the solution for you, and then I may leave the hard copies in the box outside my office, and you all can grab them at your convenience. Okay, homework 6, which is your homework on columns. I do need everybody to pay attention to this. So I'm giving it to you today. Okay, it will be due when we get back on Wednesday, but let me say maybe, because it depends on where we get today and where we get on Monday. After today, you will definitely be able to do problem 1 and problem 2. Problem 3 is the design problem. I'm not 100% will be there by then, so I may push it back. I mean, worst case scenario, it's due on the 29th, but best case scenario for you, I'm pushing it back a little bit. And it'll probably have to be that Monday, because after that Wednesday, we're headed to the Virginia's conference. So, but we'll figure that out as we get to it. So let me go ahead and hand that out. And the sign-in sheet's going around. 1, 2, 3. We're leaving the day after the 29th. We're leaving on the 30th. Oh, yeah, we're going to have to be here pretty early. Like, I think the plan is to leave like 6 something. 1, 2, 3, 4, 6. I think that's enough. Mr. Lewis. Yeah, so if we don't get where we need to have the homework done by Wednesday, I'll push it back some. All right, sound good? A couple announcements, further announcements. So your exam is on Wednesday, March 15th. We're canceling class on the 17th. One other thing, I mentioned that event happening on campus next Wednesday. Did word get around? Do you all know who's coming? Yeah. So there's food and there's the governor. So, if you
Actually learn more about the event itself.
Well, the email said they wanted to sort of keep it secret, like the email from the college, and then the university sent something like, he's coming. I'm like, well, secret's out now. So if you're interested, that's Wednesday at noon. There's food. So yeah. Okay. Any questions? I have no idea. I'm going to take a wild guess and say the answer to that question is no. What? They're doing it in the lab. I know that. The big one. No. Speaking of, let's talk about column strength. All right. Any questions? All right. Let's get back to this, because I really want to make a lot of headway today on column analysis and hopefully get into some column design. So if you recall, what we've talked about with columns are, we've talked about the behavior, and we've said there's 2 reasons why column behavior deviates from the theory, and that's what? What's the first one? Imperfections and locked-in residual stresses. There you go. So what we do is we say, all right, the model that you see here on this slide is intended to account for those effects, for geometric imperfections and residual stresses. Now, there are 3 methods for computing column capacity. There's using the equations, and there's using a couple of the design aids. And we're going to take the same column and calculate the capacity 3 different ways. One of the things we need to talk about right now before we get into the column is, and I mentioned this last time, is a note on slenderness, and that is that if we're talking about a particular column, it's not about strong axis versus weak axis. I mean, yeah, you need to know the difference, but it's really about which direction has the largest slenderness value. When you compute a column's capacity, you are computing based on the largest KL over R. So if you have a column like this, yeah, you would think that Rx is always bigger than Ry, so all you need to check is the weak axis, but because KL over R may be bigger in one direction than another, you have to check the whole thing. And speaking of, we're going to take this column, split it up into an analytical model for the x-axis and the y-axis, and just to sort of demonstrate what's going on, let's analyze this column. So we have a column that is a W14 by 90, grade 50 steel. We've got the strong axis bracing and the weak axis bracing, and we're going to determine the capacity. Like I said, we're going to determine this capacity 3 different ways. So, any questions? All right, then let's sort of get into it. Okay. Now, before we start doing the math, we're going to need some properties. So I'm going to ask for a few properties on a W14 by 90, so bear with me. If this will open. So while we're waiting for this to open, everybody turn to their table 1-1 because I'm going to need some properties for the W shape. Goodness gracious, this is taking a while. All right. There we go. I think something's happening. I think it's got a pulse. Of course, I say that, and it's still doing its thing. All right, there we go. My goodness. There we go. All right. So first thing I need are some properties for the W14 by 90. Okay. Now we're computing these from table 1-1. Or we're not computing them, we're just looking them up. Okay. I need some values. So tell me, what is the gross area for a W14 by 90? 26.5 what? There we go. All right. What is Rx? .14 inches, right? Okay, what is Ry? 3.7 inches. Okay. Now, I'm also going to look up some new ones. I'm going to look up lambda sub f, which is just BF over 2TF. And what is that? 10.2. And I'm going to look up lambda sub W, which is H over TW. 25.9. Sound good? Okay. So those two quantities are a measure of how flimsy, if you will, the flange and the web are. The larger those values are, the more flimsy the flange or the web. So what I'm now going to try and ask is, are the flanges and webs too flimsy? All right. So I need to check those values against a given limit. So do you all remember the slenderness limits? Remember it was in Chapter B. It sort of looked something like this. Y'all remember that? What is the slenderness limit for a flange? Well, I tell you what, I'll tell you the flange, and then you tell me the web. So we're going to call these compactness limits. I know it's Friday and everybody's still waking up. all right? I'll give you the flange. The flange one was 0.56 square root of E over Fy. Whoop, I can do better than that. Do you all remember that? Did you all tab that? What's the page number? 16.1-16. I want everybody to turn to 16.1-16. You turn into 16.1-16?
This is my book.
Are you turning into 16? He's like, let's make something clear. All right, is everybody on 16.1-16? What's that? All right, does everybody see where I'm getting at? Y'all remember that now? On the page on the left, case 1. Y'all remember that? Okay, now if this is the one for the flange, tell me what is the one for the web. I want you to interpret the table. There we go. And there's also a fair amount of positive reinforcement too. I heard people saying, good job. Good job. All right. Everybody got that? Oh, okay. All right. Okay, so let's do some computations. So 0.56 square root of E over Fy, what's E? I heard somebody kind of say it. 29,000 what? There we go. Units. And Fy is 50.
50 what?
No, but there's another stress value though. So what is that? Do I have a second on that? Okay, so let me make sure everybody can interpret what's going on with this, okay? This is the limiting slenderness value for a flange. Now, what is the actual slenderness of the flange? 10.2, okay? So this is a measure of how flimsy our flange is, and this is our limit on compactness. So this means we're good. Now again, if you violate this limit, it does not mean that if I place a feather on the column, it explodes, okay? All it means is that we have to use a different section of the specification. So we're good here, all right? So if we've got this one, let's do the next one. So 1.49 square root of 29,000 KSI over 50 KSI. 37.57. What? I got 30, yeah. I have a second on that one. All right. Now, lambda sub W is 25.9. So this means our web is stocky enough. Okay, so I've been using the word flimsy, but really what I need to be using from a terminology standpoint is this comparison would indicate that our flanges and webs have sufficient compactness, that they're compact enough. And compact just means that they're stocky enough. If I would violate this, it would mean they're too slender. So all this means is that section E3 applies. And if we violated this, we would just go to section E7. That's all that means. Okay? And I'll go ahead and put over here on the left that this is table B B4.1a. Is that? Yeah, B4.1a. Okay. All right. Everybody with me so far? E7. Yeah. Yes.
In the manual in the table, how do we know we're using that?
How do we know in what regard?
Like the 0.56.
What? Like, why are we using the 0.56?
Yeah.
Okay, what is the description of case 1?
Flanges of rolled eye shape sections, plates projecting.
Okay, so stop right there. So we are talking about the flange of a rolled eye shape. We're in the problem, we're doing a W section. So it is an I-beam is what I'm getting at. If we're doing an angle, for instance, we'd use case 3.
Okay.
You see what I mean? That's a good question. So what's the difference between that's for concrete. What's the difference between a rolled section and a built-up section? A built-up section would be if you're taking plates and welding them together to create an eye shape. This is rolled directly from the mill. So a plate girder is a built-up section. Yeah, well, let me say this. If I give you a plate section, then you'll have to use case 2. So, yes.
Maybe I'm the only one that's thinking, what's section E7 apply?
We're going to get ready to talk about that. All right. Speaking of that, so let's go to chapter E. Oh, we turned to this. Yeah, no. When I have chapter like chapter D, chapter B, chapter E, I'm talking about the spec back here. Like, remember, chapter D was where the shear lag table was. Like, you're currently in chapter B. Like this table right here, like you're turning the wrong way. Like, that's chapter B. That's the shaded portion. That's the commentary. Not necessarily, but I'm trying to answer his question. Who's having a hard time finding chapter E? Okay, we're on 16.1-31. Do y'all see what I mean when I say chapter E, chapter D, chapter B? When I have chapters and I have letters, I'm talking about the specification. Now, I want to turn to 16.1-31. Okay? Do you see where it says the chapter is organized into the following sections? Okay? We are using section E3 because we have a compact section. If not, we would be using section E7. Okay? Now, that's further illustrated if you turn the page to this. So turn the page to that user's note. All right. Does everybody see that? You're in the commentary. 16.1-32. Okay. All right. Look at the user's note. All right. Would you agree we're dealing with that first cross section? Okay. All right. If we have a section without slender elements, we're going to be using section E3. If not, we're going to be using section E7. Everybody see that? Okay, and I mentioned that last time. The E4 is if you're trying to ascertain whether or not the column is going to twist. And the only time that's ever really a big concern is if your column is not symmetric. In other words, one flange is bigger than another, which isn't the case for a W14/90, but might be the case on a built-up section like a plate girder. See what I mean? All right, with me on that? Okay. Now, if you're in section E3, okay, you see these equations right here on the right? You see these? Okay, these are the equations we're going to use because it's under E3, okay? If you're in E7, just turn the page a few times. And don't worry, I'm going to give you an example on how E7 would work. But E7, it's just a little different. I mean, I want you to turn to E7. Turn to 16.1-40. Does everybody see, bless you, does everybody see this equations on 16.1-40? Do you notice something different about those equations? There's a Q in them. Does everybody see the Q? Okay. You do or do not? Okay, okay. The Q is just a reduction factor to account for elements that are slender. Okay? So that's the only difference. Okay? What's that? What's flow rate or heat? I don't understand. I don't do flow. Pressure. Head. What are these things? No, it's Q allowable. It's bearing capacity. That's what it is. All right. Did I answer your question? Yeah. Yes. Is everybody else okay with this? Again, if you have a section that has slender elements and you place a feather on top of it, it does not mean that it explodes. Okay. Now, for us to use section E3, does everybody see in section E3 that there's a lot of KL over R terms, right? We need to figure out for this column which KL over R we're going to use. Okay, so we need to do some work on slenderness. What's that? Well, even if we did that, F sub E is a function of KL over R, so we still need the KL over R values. All right. Now, we talked about this last time. If you recall, if we look at the x-axis, right? If we look at the x-axis, we have a single unbraced segment that's 35 feet long, right? But if we look at the y-axis, we've got 3 unbraced segments, right? 1, 2, and 3, right? So what I'm going to do is I'm going to handle each segment individually. Sound good? All right. So here, let's adopt a naming convention right now. We'll call this the X segment and call these the Y segments, Y1, Y2, and Y3. Sound good? All right. So you help me out with this. So I'm going to draw a little table here, and let's see if we can figure this out. So case, and so we have the X case. There'll be 1, 2, 3, 4 more columns after this. So like 1, 2, 3, and then maybe like that. Okay. So we have the X case, and then there were 3 Y cases, right? So Y1, Y2, and Y3. Okay. So to compute KL over R, we need 3 things. That's going to be crazy. We need a K value, we need an L value, and we need an R value. Wow, I know. So we're going to take each of these one at a time. So we're going to have K, L, and R. So let's start off with the simple one. Let's start off with the R value. Okay? For the X case, what's the R value? What's that? Because I'm dealing, oh my goodness.
Trust the process.
Yes. Believe in me. Say that again, say it loud. All right, the question was, what is the R value across the x-axis? And it's Rx 6.14. Now, that's not technically correct. It's 6.14 what? All right, that matters. For the y-axis, what are they? No. 3.7? There, okay. Okay. Now, everybody with me so far? Now let's do the lengths, okay, the length. So let's deal with the x-axis first. What is the length of that segment? There we go. Exactly right. So the length along the x-axis is 35 feet, but that's in feet. So converting that to inches is, there we go. All right, so, wow. Okay, y'all see where I'm getting, why I'm doing that? I put the radius first because in inches, so the lengths need to be in inches as well. Okay, now the y-axis, we're going y1, y2, y3 from the top bottom, so from the top down. So what were the lengths from the top down? 10, 15, 10 in feet, so converting to inches, it's what? 120 and 180? So ly1, ly2, ly3, so 10 feet, 15 feet, 10 feet. All right. Sound good? Okay, now, the K values. Now, before we even start looking up K values, where do you find K values in the manual? You tabbed it, right? Now, you've caught up.
It's in the column section, right?
No, it's way back. Well, table CA71 on page 16.1 dash what? 511. So you're way back in there. 16.1 dash 511. Start to notice the columns that you need to have some tabs, right? Yeah. Along with the manual. Hold on, wait. Buddy system. And over here, I hadn't forgotten. What's that? Okay. All right. Let's take the X segment. So looking at the column on the example, what is the bottom boundary condition for that column? And the top? No, I'm talking on the example. But okay, you're bringing up a great question. It's allowed to translate, or it's prevented from translation, but it's free to rotate. So that's going to be a pin boundary condition. So if you have a column that has a fixed bottom but a pinned top, what is the K value? No, somebody said 0.7. 0.8. Oh. What are you asking?
Is it 0.8 because we got like the lambda RF bigger than the lambda?
No. It is 0.8 because 0.7 is the theoretical value, 0.8 is the recommended value for design. So this is a KX.
When you use the theoretical?
We don't.
Ever?
No, I'm serious, we don't.
Then why do they put it in here?
Just so you can match it with what you learned when you took deformables, because in deformables, that's what you learn. No. All right. So this is the K for the X in the X direction. Let's do the Y direction. So from the top down. So the top is pinned. And what's the K value? 1, then 1, and then no.
0.65?
No. 0.65 is assuming fixed and fixed.
What section are we on?
We're looking here, but we've got to look at the column. See, this is pin. Does that make sense?
So that's 0.8.
For the bottom one, yes. So this is KY1 is 1, KY2 is 1, and KY3 is 0.8. Does that make sense? I'm serious. That is this. What we're talking about here. This is incredibly important. Like, if you understand this, then everything we're about to do is pretty rote and pretty methodical. But you've got to understand this. This is incredibly important. Any questions? Because this is. What do you mean we didn't need it? This is the simplest one. Yeah, it is. This is the simplest part. All right, is everybody, seriously, does anybody have any questions about what we've done so far? Well, if you understand that, then I want you to compute KL over R for each row, okay? So K times L divided by R, K times L divided by R, et cetera, et cetera. And let's start writing them down. So the top one, what's the top one? Let's do one more decimal point, 54,723. Okay. The next ones. Wait. What? This one? The one on the bottom. I got 25.946. That. All right, hold on. The second one, the one that's right here. What's that?
I got 32.4432.
32. Okay, this one. 649. Now this one. Okay. Do we have seconds on the table? Okay, now, wow, I don't know what's so funny. For this given column, and for any column, a column's capacity is a function of its slenderness. The more slender a column, the weaker the column. So when I compute the capacity of this column, which value do I use? No, the largest. The more slender a column, the weaker the column. So we are calculating slenderness. There we go. Does that make sense, though? Okay, so this one governs. Now, I have to make a very important point, and I really need everybody's attention on this. Does everybody agree that the top row is the largest? Okay, that's simple, right? Now, let's also, there's another important point. Which axis governs? I don't know what just happened. So. Oh, okay, is everybody okay with this? Okay, but the point I want to make is that the strong axis governs. Okay, what matters, this didn't matter that Rx is bigger than Ry. What mattered was that this slenderness was the largest value. But I want everybody to remember in the back of their head as we do these examples that for this column, the strong axis governs. That really matters when we look down the line. Everybody good? Okay, it will make sense. Just bear with me. All right, if you understand what we've done so far, then using the equations in the manual are incredibly simple. Everybody got this? Okay. So, okay, to compute the column's capacity, we're going to take it one step at a time. So the first thing that we're going to compute is elastic buckling stress. Okay, so that is Fe is pi squared E divided by KL over R squared. So that is pi squared times 29,000 KSI divided by, now what's KL over R?
54.
There we go. 54.723. But we take that quantity and square it. So don't forget to do that. So what do we get?
95.5.
So we'll say 95.58 KSI. That is not the maximum stress that this section can handle. I mean, it's only grade 50 seal, so we know it's lower than that. That is just a useful parameter for what's coming later. Is everybody with me on this? Everybody good? Now, so that you understand why I computed that value, I want to pull something up. If you recall, this is essentially our model right here. This is the curve that we're using to determine the capacity of a given column. So we've got KL over R figured out, right? It's 54.723, right? Now, regardless of whether or not I use this equation or this equation, I needed FE. Is everybody okay with that? Okay. Now, which equation do I use? Well, it depends on whether or not KL over R is bigger or smaller than that, right? So let's compute that, okay? So here's what I'm going to do. I'm going to say, we'll call this critical buckling stress. So KL over R is 54.723, and 4.71 square root of E over Fy is 4.71 square root of 29,000 over 50, KSI and KSI, which is what? 113.4, something like that, right? So, based on these two numbers, you tell me, how do I compute F critical? I'm not going to pull it up. I'm going to make y'all do some work. What's that? The equation on the left. Now, what's the equation on the left?
Dude, I think you did that part.
I thought you were saying like just use the correct equation.
Nice.
They're right.
Now, hold on. Whether or not you go in Chapter E or you look at the first slide in your handout or...
Oh, shoot. There we go.
Oh, yeah.
Yeah, that .658, I can't read that. It's so small.
Okay. Fy over Fe. Okay? It's like I'm making you all do work and like look through your notes and read. I'm horrible, aren't I? What's that? Your pages are. So 0.658. Now, again, it's not multiplied by this fraction. We're raising it. Okay. All right, guys. Let's get back on track. Okay. Now, so what do we get here? Oh, God, that on me, man. What's that? Did you multiply by the fraction or did you raise the fraction? 40 point what? One. I got 1.7. That's 95.58. Is that? Has everybody got this? Okay. All right. If you've got this, then therefore our design capacity. All right. Phi PN is phi times, all right, so first off, what's phi for columns? First off, you shouldn't have to guess. You should be able to go to chapter E of the spec and. My facial expression, though, can't be called into evidence, you know. All right, so 0.9 times F critical times AG, so 0.9 times 40.17 KSI times, what's AG? All right, there we go. So phi PN is what? So phi C. So instead of phi sub T for tension, phi sub C for compression. What is this? Yes, point what? 0.1? So 0.1. What? Now hold on, guys. I know you all are hyper, and it's Friday and it's rainy. Is ever well, not. It took a while. we got to maintain some focus here. So are we good? Does anybody have any questions? I'm saying this is important. Okay. That was this. Okay, that was this right here. Okay. We computed the limiting slenderness value and then compared that against the slenderness for the flanges in the web. These values are these? Yes. You'd still use E7. Yes. Because that means you have a slender element. That won't happen. No, seriously, that won't happen. I mean, and it won't happen. Yes.
Is there a name for the value of 4.71 of the square root of fraction G over unit 1?
We call it limit. I don't know. There's no, not really.
Because for some reason I named it FCR, and then you're FCR, and also named it.
No, that is not FCR. That tells us how to compute FCR, okay? All right. Any questions? Okay. Now, this is important, okay? I want to pop quiz you on something. Which axis governed this column? Okay. All right. Strong axis and the x-axis are the same thing. My goodness. It actually doesn't matter. It actually doesn't matter. I'll explain why. Let me go ahead a little bit to this right here. Okay, so does anybody have any questions about this example? Okay. The next method is to use the column capacity table. Now, I want everybody to turn to this. If you haven't already tabbed it, you need to do so. Okay. So we're on 4-12. This is a very important table for the use of design. Okay? Now, what this table will do is it will tell us, based on the length of a given column, okay, it will tell us the capacity, okay? Now, the length, however, is very important. I want somebody to read what it says right here. So that means you have to, use your manual. You can't read it off the slide. What does it say?
Effective length KL B with respect to least radius gyration R1.
R what? Y. Okay, so let's be clear. This table was generated based on the assumption that the y-axis or the weak axis governed. Is that the case for this column? No. Okay, so we have to do something a little different in order to use this table. First off, in order to use this table, we need to have the ability to linearly interpolate, which I hope everybody in here you're experts at linear interpolation, right? Well, oh, come on. You can linear. Yeah, well, yeah. Okay. All right, so let me explain how we go about this, okay? So this table was written based on the assumption that the y-axis governs, okay? That's not the case for this column. The strong axis governs. So what I'm going to do is this. I'm going to try and compute an effective length that we can use for this table. So if you notice, the way this table works is you have a given KL value, right? You have a given KL value, and then based on that KL value, you look up the capacity, right? Now, if the weak axis governs, it's simple. If it's KL of 14 feet, find 14, and there's your capacity. But if the strong axis governs, what we're going to do is we're going to transform it a little bit. So we're going to take that KL and we're going to divide it by the ratio of Rx over Ry. And the way I came up with that was just basically to say KL over R in the X direction equals KL over R in the Y direction and solve for that. Okay? Now if you notice, look at the bottom of the table and what do you see? Rx over Ry listed. Everybody see that? Okay. So what we're going to do for this column is we're going to check it using the table. So let's be clear. To use this table, this is how it works. And I want everybody to be clear on this. If the weak axis governs, just go into the table with KL. Okay? But if the strong axis governs, go into the table with KL divided by the ratio of Rx over Ry. Everybody okay on that? Okay, don't worry, we're gonna try it out on this. All right? So let's see what happens when we use this this table. And we can finish this pretty quickly. What? This is the riding mower. All right? So example 15B. Guys, got to maintain some semblance of order. All right. So let's recall from 15A. Okay. Now, we said that for 15A, first off, what's the section? 14 by 90. What was the K value for the section that governed, for the direction that governed? What was K? 0.8. What was the length? It was 420 inches, right? But if you notice, the tables or the lengths in that table are listed in feet. So what I'm going to say is this. I'm going to say it was a W14 by 90. KX was 0.8. And the length was 35 feet. Sound good? So since this is a W14 by 90, help me out. What's the Rx over Ry going to be? So what that means is you're going to have to find the Rx over Ry for a W14 by 90. And what is it? 1.66, you said? Okay. So Rx over Ry is 1.66, and you got that from table 4-1. Is everybody with me? What's that? Do you know where the W14 by 90 is? You're on W14 by like 370. You need to turn.
Oh, okay. I didn't know.
So W14 by 90, and then down. All right. Now, what I'm going to do is I'm going to compute an effective KL. And I'll admit it's probably not the best length because it's like an effective, or the best name because it's like an effective length. But that's sort of what I'm calling it. So KX LX over RX over RY. All right. So help me out. What's KX? Make sure y'all pay attention. 35 feet over 1.66. Okay, and what do we get? $16.87, you said? So, everybody with me on that? Okay, so if I go into this table, I need to use some linear interpolation, right? Is there a value for a length of 16.87 feet? No, but, what, yeah.
Possibly like, you get like in between,
Because we can linearly interpolate. And first off, to be conservative would be to round up to the 17 feet, but here's the thing. The purpose of doing this is to see if we get the same capacity. You're not going to get the same capacity unless you go through and do the math. So, does that make sense? What?
So in the homework you want to linearly interpolate?
Yeah. Yep. I do. All right. Okay, so we're not going to be able to look up a value for 16.87 feet, but what are we going to be able to look up?
16 and 7.
Okay, so what is phi PN for a KL of 16 feet, and what is phi PN for KL of 17 feet? So what's the 16 feet? 979. All right, and what's the 17? Okay, do those values make sense? I mean, what did we do? What did we get when we did the math? Like actually, 958. So does that make sense? Okay, so to linearly interpolate, all we would do is say our phi PN, and then we'll call it, is, what would we do? 979 kips plus, then we do our change in x, so 16.87 feet minus 16 feet. And then we have our change in y over change in x. So 17 feet minus 16 feet. And then we've got 955 kips minus 979 kips. So what do we get? I mean, that's just linear interpolation. I know you all can do that. 958.12, you said? So 958.12. The point, so Will, the point is when you're doing an exam, what I'm giving you, right off the bat, I'm giving you two different completely separate ways to analyze a column, and you get the same answer. So you've got to interpolate to do that. Do you see what I mean? Sound good? All right. Any questions? Yes. No. No. You've got to know. What? Well, what if Fy was 40 KSI? Look at the top of table 4-1.
I guess you can't comment too. Is there no linear interpolation or anything for that?
It's too nonlinear. You can't do it. Yes, it is. Hey, there you go. Now you're thinking. Exactly. If you've got different yield stresses, maybe you could use table 4-22. We're out of time, but example 15C, we are going to use table 4-22. real quick before we end it, we're not going to talk about columns for a while. Right now, you should be able to do problem 1 and problem 2 on the homework. By Monday, you should be able to do problem 3. So when we come back from spring break, like we get down to business, getting back to columns, I know margaritas and Mai Tais, and you'll be like, oh, back. No, we're getting to it. So like today was a little out of it, but we're going to get back to business. I mean, next Monday, we have exam review, and then we have our exam on Wednesday. So, yes?
So we're doing exam review and then still talking about columns?
No, we're not going to come back to columns.
Monday after break.
Yeah, we're not going to come back to columns till after break. So, like after break. Yeah, I did. All right, I'll get it here in a second. All right. That's all I've got. I will see you all who are not in concrete next week. You all have a good weekend. We'll see the rest of you all here in a few minutes.